Good morning, welcome. We have been looking at implicit methods. So the implicit Euler method was our first choice. That's the first order method, it's very stable. And now we want to see others which are more accurate but have also other features. We'll see that. And the method that we'll discuss next, the trapezoidal method, is actually one that you're going also to study and to use in exercise 3. So how can we get that? There are different ways. One easy way is simply to take the arithmetic average of Euler's method, explicit method, and the implicit Euler method. Then we get the following, and then that actually is then the trapezoidal method, so we can say that also. That is the following. We compute the solution at the new time level, n+1. By using the old one and adding the average of the slope, which is our function f, at the old time level. And that was actually used without the half for Euler's method, the explicit one. But now we add also the function evaluated at the new time with a new solution that we do not yet know. And if we just would take this, not take this, take away the half, we would have the implicit Euler method. So then you see here that is what we argued in the beginning, the arithmetic average of the explicit Euler method and the implicit Euler method. But since it contains this here, it is an implicit method. So, we can show again by local, we can use Taylor expansion and show that the local truncation error is of third order. So, local truncation error. N is order h to the power 3. So it's one order higher, more accurate than both explicit and implicit Euler method. And from that we get the global error by the argument that we had taken before. And that is then the number. Global error, it's the order of the method, is order h squared. So that means it's a second order method. So that's the improvement with this method. It is more accurate than both the explicit and the implicit Euler method. Now we also want to study stability for this method to see also the properties that it has, and that is also something you will do then in exercise 3. And we do that as usual for the test equation. The test equation is, as you know y prime equal lambda y, where lambda is a complex number and constant. And we assume the initial condition equal to 1. I got now a question, why do we do that yesterday? And the argument is, if you just do the first step, starting from the initial condition, 1, you get the amplification factor directly. But we do it the way that we take, we go from time level n to n plus 1, and then we see it also from there. So then we do that. So we apply now the trapezoidal method to solve this test equation. So then we get the following. We get then that we get yn plus, and now it's usually we just take h here. It's not important to look for the local time steps. And then we have here lambda yn. That is what we get from the f here. That is lambda yn, and this will be lambda yn plus 1. So, and it is now a good idea to collect everything that we don't know on the left-hand side, that is yn plus 1, and all what we know on the right-hand side. So that means that we can get this one to the left-hand side, and then we get 1 minus, that is lambda h half, that is then, see, we factorize the yn plus 1, and on the right-hand side we can see that we can factorize also the yn. So we get 1 plus lambda h half divided times the yn. And that is also what you're going to do in exercise 3 for the first problem there. First you write down, it's a little bit more complicated, but just a little bit, that ODE that you have there, but then you collect everything unknown on the left-hand side, like here, everything known on the right-hand side. And then we see immediately that we can express then the yn plus 1 as what we have on the right-hand side is the 1 plus lambda h half, and when we divide by that, it's 1 minus lambda h half times yn. So from that we already see the amplification factor, and what I mentioned before, if we would just go from time level 0, initial condition, to time level 1, that would be 0, and then the y0 would be 1. So then this we would get the amplification factor directly. So but we do it in this way, and we also like to see what it means when we have this form. It means that we can compute the solution at time level n by taking this amplification factor to the power n. So that means that we get that yn can be expressed as this factor 1 plus lambda h half divided by 1 minus lambda h half to the power n. Here we would have times y0, but that is 1. Also got a question why it was for Euler's implicit Euler method. Why do we have that? Well, you just use this formula again on the yn. So the yn is then equal to this factor times yn minus 1. So we can go down then in this way, and if we do that for n, we will get this factor n times, therefore to the power n. So the last one will be y0, but this is 1. So then we have this form, and from that we can then see immediately, and we could have seen it already before, that the amplification factor is this one. it's not necessary to write this. I write it just for completeness, but it would be enough just to do this analysis here and to argue that the amplification factor is the ratio of yn plus 1 to yn. We have this factor. So the amplification factor of the trapezoidal method then is, call it G of lambda h is equal to this ratio of 1 plus lambda h half divided by 1 minus lambda h half. So that is what we get. And then we can easily get from that a stability condition. Because we see from this, if we multiply that, let n go to infinity, it will get only bounded if the absolute value of the amplification factor is smaller or equal 1. That is our stability condition. So, then we write that. The general condition is that the absolute value of the amplification factor has to be smaller or equal than 1. And that means that for us here, for the trapezoidal method, that the absolute value of the ratio of 1 plus lambda h half divided by 1 minus lambda h half has to be smaller or equal than 1. And that we can also express again using stability domain, and that will be the stability domain then of the trapezoidal method. It turns out that is equivalent to saying that lambda h is in the stability domain of the trapezoidal method, which turns out to be all complex numbers. And now it gets very easy, for which the real part of the complex number is smaller or equal than 0. So that is not obvious. So we can now do a little proof of that. And we can do it in such a way. Now I did it for the following. We assume that lambda h half, that is our constant from the test equation, this lambda, which is a complex, times the step size h divided by 2, we assume that that has a real part x and an imaginary part y. That's just an assumption, but that's reasonable because it's a complex number. So x and y are real. And now we want to use that if we have something in absolute value smaller or equal than 1, it is equivalent to saying that the absolute value to the power squared is smaller or equal than 1. That's, we can argue both ways, because taking this to the power 2, that makes things a little bit easier. So let us see how that works. So now we look then for the absolute value of this squared. So then we have the 1 plus lambda h half divided by minus lambda h half to the power 2. And now we write then what we assumed for lambda h half, that this has a real part x, so we get then 1 plus x, and we get plus I y. So that is simply that we write for lambda h half, we write x plus I y. Real part plus imaginary part. And in the denominator, we get then 1 minus x minus I y. And that is taken, we should take that in absolute value to the power 2. And now we simply have to know about complex numbers. How do they, what's the absolute value of a complex number? That is the real part squared plus imaginary part squared. We can do that both in the numerator and the denominator. So then we get what is the real part? 1 plus x. Imaginary part is y. And in the denominator, we have 1 minus x is the real part. And the imaginary part is minus y. That squared is also y squared. And that has to be smaller equal than 1. That is the condition, the stability condition. Now we can multiply by the denominator and see that this is then equivalent to saying that 1 plus, now if we compute the binomial formula we take here to compute this 1 plus x squared. And we do it the same also for computing this squared when we multiply it. So we get 1 minus 2x plus x squared plus y squared. And then we see most vanishes. So we have the 1, the x squared, the y squared, the 1, the x squared, the y squared. So that means we get in the end that this is equivalent to saying we take the 2x also to the left hand side. It's equivalent to 4x smaller equal than 0. Now we can identify what was the x. The x was, we see here, the real part of lambda h half. That means 2x is the real part of lambda h. That means 4x is 2 times the real part. So that's 2 times the real part of lambda h. That's be smaller equal than 1, and we can easily divide by 2, and then we see what we claimed at the beginning. Because this is then the requirement that the real part of lambda h has to be smaller equal than 0. That is what we get here. So that is then our proof. And that means, regarding the stability domain, that it is now containing the complete left half of the complex plane. Because the complex plane is real and imaginary numbers. All that have negative real part are now inside the stability domain of the trapezoidal method. So if you plot this, you are also asked to do that in exercise 3 for the 3 methods that we study: explicit, implicit Euler method, and this one, the trapezoidal method. And then we see that here we have the origin, and all on the left-hand side of this, of the imaginary axis, that is our stability domain S of the trapezoidal method. So it's fairly large, and it means that we can essentially compute all stable ODEs with that. Because with stable ODEs, the real part of lambda will be smaller equal than 0. Multiplying by h doesn't change that, so then we are fine. But there is a thing that you should be aware of, a fact that you will also see when you do the experimentation in exercise 3, when you play a little bit around with the methods and with the time step, you will see following. If we take the limit for the time levels to infinity, that means that we go over essentially all very long time and let that the method compute many time steps. We do that for let's see. No, that is, I think here I did a wrong thing. It's not n that we let go to infinity, we let the time step. Sorry, that was wrong. we let the time step go to infinity. We try to take a very large time step. That's allowed by the method because even if h is very large, and if we have the lambda, it has negative real part, we can essentially multiply it by any large number. It's still stable. So what does happen then for this method when we let the time step go to infinity? We have the amplification factor, we derived that. It's 1 plus lambda h half divided by 1 minus lambda h half. And unless lambda is 0, we get here minus 1. Because if this is dominating, in the end this is dominating, then that will determine what is going on. So then we can, if you want to derive it, the one first we can neglect compared to these. That is too small. The 2 here, that cancels. And what you get in the end is minus 1. If lambda is not 0. And in our case, it is relevant for the real part if we are looking at stable ODEs that are smaller than 0. It would also be okay for lambda greater than 0, but this is the interesting one for us. And that is the situation that we usually have. So what does that mean when the amplification factor is minus 1? It means that you jump from plus 1 to minus 1 in each time step, from one to the next. That means you get oscillations. And that is also what you will observe in the computations, that the trapezoidal method tends to have oscillations when you take large time steps. Something that we don't like. So the method is more accurate than the implicit Euler method, but it is in this sense not as good. So when you want to have a stable method, then you use implicit Euler method, not this one. If you want to have good accuracy, you can use the method, but you have to control the time step. That doesn't get too large, because then you run into this problem. So, therefore, we want also to know a method that is both higher order and that has what we call robustness, so that doesn't have these oscillations when we would take larger time steps. And the one that people like to use, for example, for unsteady aerodynamics, people use this method that we'll see now, also in other situations, and we'll see also later on. It is also part in one of MATLAB's inbuilt functions that is called BDF. That's an acronym. Let's see that now. So the method, first I write the acronym because it's best known for that. The BDF2 that we are going to study. And that is the second order. That is the acronym backward differentiation formula. So it is the BDF. So the idea of this method is that we approximate the y prime, the derivative of y in the ODE, to higher order. We argued with the implicit Euler method, we approximate it by first order. backward difference. Now we take a second order backward difference. So the idea is that the y prime at the new time level, as in the implicit Euler method, when we compute the ODE, y prime equals f of ty is approximated by a second order backward differentiation formula. By the backward difference, backward difference formula. And that is the following, that you can also derive by Taylor expansion to show that this is really a second order approximation. And it is 3 times yn plus 1 minus 4 times yn plus yn minus 1 divided by 2h. And here, so that is the first thing, that is the formula that you'll have good use of also when we talk about PDEs, boundary conditions, for example. But here it is for getting a good approximation, a second order approximation at time level n plus 1 of the first derivative. And then the right hand side we take then also at this time level. That is important. It's taken at the new time level with a new approximation yn plus 1 that we don't yet know. So that is the second order backward difference formula applied to solve the ODE. And one thing also is to note here that we don't write here hn, because we have now, that is the new thing, we have now 3 time levels involved. Before we had only time level n and n plus 1 involved, now we have also n minus 1. So therefore we are no longer free to choose the h, the time step, as we like, as we go from n to n plus 1, because we have already used it before. So that is one thing. So note we have now 3 time levels. 3 time levels are involved, n plus 1, n and n minus 1, and we have that h is now no longer, we can no longer choose that, so h, not hn. And the other thing is that we have to be aware of when we use this method later on. When you start the method, you cannot do it, because when we start, we know n is 0, then we know y 0, and we want to compute y1, but we don't know y minus 1. So we need a method, this is a 2-step method, because we need to step from n minus 1 to n, first step, and from n to n plus 1. What we need a 1-step method, as we had before, for example, the trapezoidal method or Euler, implicit Euler method, to get this started. So then we compute from the initial condition y0, the y1, then we have that, and then from time level n equal 2 on, we can use that. So that is also, that is involved here. It has 3 time levels, it has a constant time step, and it needs another method to start. So, and from that, then we can write the formula of the method. So, from using this approximation that we just applied, we get then the formula of the PDF2, and if we write it in the form that we have been commonly using, then we would simply multiply by 2h and divide by 3, so that we have the yn plus 1 on the left hand side, and we put the rest on the right hand side. So then we would get yn plus 1 is equal to 4/3 yn minus 1/3 yn minus 1 plus 2/3 h times f, slope of that we have for this for our ODE at a new time level and with a new solution n minus 1 that we don't yet know. So that is the form of the BDF2. There is another way to write this equation that is actually used in CFD, and that is not to write it in this way, but to write it in so-called delta form, that we look at changes from time level n to n plus 1 and likewise from n minus 1 to n. That is so-called, we can write it in this form or in the form is so-called delta form. That is the following. When we introduce the difference, then we call that delta yn. So delta yn, that is the difference between n plus 1 and n. So you see, if we subtract here the yn and take that to the left hand side, we get 1/3 rest. So then we get the delta yn on the left hand side. We have then 1/3 of delta yn minus 1 on the right hand side left. And this is unchanged, the 2/3 f of tn plus 1 yn plus 1. With that formulation, the expression gets a little bit easier. And in here, the delta yn is the difference between the solution at the new time level n plus 1 and the old time level n. So that is what we can do here to give it another form. As already mentioned by the name, the method is second order. That means the local truncation error is of third order, and the global truncation error, which is the En, is order h squared. So in that case, it is the same order of accuracy as the trapezoidal method. Stability is a little bit more complicated, and that is because we have now 3 time levels involved. Before, we could compute the amplification factor, as we saw for the trapezoidal method just before, very simply. But if we would do that here, we see here that we have also the time level n minus 1 involved. And that would lead actually to a polynomial for g. So that gets more complicated, we skip that. We just write the solution regarding the stability domain. It turns out that the method is stable. The BDF2 is stable for lambda h in the stability domain, and that happens to be the complex plane without, I call it D2 as the disk 2, and D2 is the disk that is all complex numbers for which the distance from +2 on the real axis is smaller or equal than 2. So that we'll plot that as now. We don't need to keep that in mind, but it might be good to have it in mind as a picture of the domain itself. And it looks like that. We have again the real axis of lambda h, lambda coming from the test equation, and h our time step. And then we have here the imaginary part of lambda h. And now we get a circle. Here we have the origin. We have now a circle around 2. So then we have here 4. We have, let's see, we have the 2 roughly here. So this is 2i. This is minus 2i roughly. So we get a circle. And this circle is not in stability domain. Everything else is. So it means everything around here up to this circle, that's all is the stability domain S of the PDF2. So it is, and that is how you can memorize it. It is almost very similar to the stability domain of the implicit Euler method. For the implicit Euler method, we had a circle around 1 with the radius 1, so it was a circle here. So this circle is just a little bit larger, but it's not interesting because we are mainly dealing with stable ODEs. That is our goal. Then we are in this range. So the method, this method, and also implicit Euler method, they are stable even if the ODE is unstable. If we are somewhere here, outside in the stability domain of the method. But the important thing is that it is more robust in the sense that it does not suffer from these oscillations that the trapezoidal method suffers of. And therefore, people like to use this method for unsteady computations, because then it is higher order accurate and it is, say, we call it robust. So now we have seen 3 implicit methods: implicit Euler method, trapezoidal method, and the PDF2. Euler, implicit Euler is first order method, very stable, robust method. Trapezoidal method is second order, but not that robust, suffers of oscillations. And this one is second order and is also robust. So when you want just steady state, as we see in CFD computations, we just start with something and go to steady state, then it is best to use implicit Euler method. But if you are interested in the dynamics, then PDF2. So there is a definition that is interesting for us regarding stability. And so if you read books on ODE methods, you will find this term. It was introduced by Bernhard Dahlquist in 1963. And it says, if the stability domain of an ODE method contains the left complex plane, that is actually identical to the stability domain of the trapezoidal method. So that means in best if all complex numbers for which the real part is smaller or equal than 0, if that is contained in the stability domain of the method, which we call always S, then the ODE method is called astable. a little bit in literature, and it seems to come from absolutely stable, this A that Dahlquist used there. So it's characterizing the size of the stability domain. So then we can just conclude by looking at our three implicit methods. Here we have one here, so this definitely contains the left complex plane, so the BDF2 is astable. And the trapezoidal method is just astable. It's just there, the stability domain is equal to the domain that we require to be inside it. So that is also astable, and of course implicit Euler method. So from using this definition, we can see then that the implicit Euler method, that the trapezoidal method, and that BDF2, they are all astable. Shown you the example for the trapezoidal method, but maybe we can do that after the break. That I take an example for the trapezoidal method. Okay, good. So, any questions so far? If not, then we take now 15 minutes break.